Okay, so we are back in action in numerical methods. The next two chapters are going to be lightweight, easy to understand, very practical and useful. And I'll begin them with a question. And unfortunately, I don't have a compelling story to tell here, a motivating story like, you know, the rocket, the Ariane rocket disaster, etc. But I do have a plot about CO2 emissions per capita, worldwide CO2 emissions versus year from 1960 to probably 2014, 2013. And each one of those points corresponds to the worldwide emissions of CO2 for that year. So 1960, 61, and or kind of more data in between. And the question is, okay, over this period of time, I'm going to ask you this, like, you know, real problem you're facing now. What is the total CO2 emissions in that period of time? What would you do? Go. Give me some ideas. How would we calculate the total emissions in that period? Discuss a little bit. Yeah. I will pick you when I. Don't worry. Don't go anywhere. If you still have your name tags, put them up, please. Come up with ideas. Maybe some of the things we've learned, you know, interpolation, regression, could those be helpful? I know your name, so. Okay, let's see. We start with Evan because he so gallantly volunteered. I heard you speak some geometric stuff.
I would say find the area under the curve, which right now I wouldn't know how to do. So I just take like linear regression to make a big triangle and find that area to get like a super rough approximation.
Okay.
I was just going to say something similar but with linear regression, but the linear regression is going to give us a formula. We just do an integration.
Okay. Okay. Nathan?
I think you need to multiply the metric from CO2 per capita by the total population of the world for every year, so you have like the total amount.
Sure, that's fine. But like, how would you add up? You know, at every data point on the x-axis, you have a y value, right? So how would you, given this graph, given the data x, y, what is the total CO2 emissions? Whether you multiply or not is irrelevant in this case. So something along the lines of what Paula and Evan said.
The time set also is 1 year, right?
Not necessarily. It's not. So this data is kind of not structured. So it might be every 1 year, it might be every half year. So other thoughts? Yes.
Would we have the actual data points?
Yes, yes, you have the actual data points, the x, y data points. Yeah. So what is, elaborate on that?
Just using.
What's a Riemann sum?
Basically, just you take the height of the point, multiply by the distance between each point. Basically, you set up a bunch of rectangles
Okay. Okay, roughly. But what if you just add the y points? You just add them up to each other, right? Yeah, because you don't have kind of that x spacing, right? What about putting an interpolant? Driving an interpolant across all of those data points, because for each x value you have one y value, right? So you could drive a linear interpolant, between every 2 points, and then apply an integral, right, between each one of those 2 points, right? Or you can take a very high order interpolant. That's going to be better than regression in this case, because regression is going to capture the trend, right? But the interpolant is going to give you a more accurate representation of the area under the curve. So all of your answers are kind of in the right state of mind on how to think about this. And we're going to implement one version or another of this, and eventually we're going to end up with this version of the Riemann sum to do the integral. Okay, at the end, learning objectives. I find that to be very, very useful for every chapter we do. At the end of this chapter, you'll be able to define what quadrature and numerical integration means. They mean the same thing, but the word quadrature historically comes from that idea of the Riemann sum of splitting this curve into rectangles, quadrilateral elements, and then adding them up to each other. Calculate the area under an analytical function using Newton-Cotes formulas. So if you're given a formula and a function like sine x e to the x, integrate that, or e to the minus x squared times square root of x. Like, you cannot do that integral necessarily by hand analytically, right? So the only way is to integrate it numerically. So we'll develop formulas to integrate these nice continuous functions. The nice thing about continuous functions is that you can evaluate them at any point you want, right? Sine x, you can evaluate it at any x you want. Now, for discrete data, we're going to also develop some Newton-Cotes versions of those formulas, but you'll find that you are limited by the data that you have. Regarding my discussion with Nathan now, like these data might be scattered every year or every half year. That is going to limit your ability to use all of the formulas that we're going to develop. We're going to learn about the left point, right point, midpoint, trapezoidal, and Simpson's 1/3 and 3/8 rules to calculate the integral of a function continuously. And we'll see which one of those, all of those rules, left point, right point, etc., which one of those are the easiest to apply on discrete data. We'll see how to do that in Python as well, so we can compare our codes to what Python is giving us. And finally, we'll just look at some upper bounds for the midpoint, trapezoidal, and Simpson's 1/3 rule. Okay. The idea of an integral is to find the area under a curve. If we are given a function shown here in red, and you want to find the area under this curve between points A and B, then you write this as integral of AB, f of x dx, just a symbol, shorthand for finding the area under this curve. Okay, the simplest way of doing numerical integration, now clearly this is assuming that you cannot evaluate this integral analytically. This is not integral sine x, right? This is integral of some weird complicated function that, does not admit a simple closed form analytical solution where you can do it by hand and then do the integral by hand and then apply at the bounds. So the simplest set of approximations or methods to approximate the integral are called Newton-Cotes formulas, and they are based on the idea that you can, rather than taking the full function and integrating it, we approximate that function, okay, with a polynomial. So that means you take 2 points, 3 points, 4 points, whatever, and you put a polynomial interpolant, like we learned how to do previously, and then do the integral on that polynomial, because it's very easy to integrate polynomials analytically. And that's the idea behind Newton-Cotes integration. We start with the simplest approach, which is called the left point rule, right point rule, or midpoint rule. Okay, and the idea here is you approximate the entire function as a constant on the interval AB. We haven't said anything about the interval AB, and bear with me, we're going to learn how we can increase our accuracy. But any interval AB, we're going to take that function and approximate our function on that interval as a constant. So you simply substitute f of x approximately equal to constant. A huge error being committed there, but we can reduce that significantly. You'll see how. So then when you do that, your integral from a to b is simply integral from a to b of c dx, which is a constant. You can pull out the constant. That gives you cx from a to b, which is b minus a times c. So in other words, it's the area under a rectangle, right? Because you approximated the function, which is the y value, by a constant value for all points. And then your interval, your horizontal side, is b minus a. And we can choose c in a number of ways. So the first way is you say c is equal f at a. So in other words, this is your c. And then the area under the curve becomes this area, right? So you're approximating over this entire interval, your entire ret function, you approximated it by this value, f of a, okay? So for all x values, for all values between a and b, your function is constant equal f of a. The integral in this case is b minus a times f of a. And that's called the left point rule, because we used the left point to approximate the function. Okay, so what is going to be the right point rule? You use f of b, right? So if you take f of b, this would be your approximation of the integral. In this case, one of them is underestimating the area under the curve, and this one is overestimating it because you're computing stuff up there. Okay. So in this case, the integral is b minus a times f of b. All right. There's one more rule. There's actually an infinite number of rules. If you assume f of x is a constant, you can pick any value in the interval, right, and use that constant as, you know, your representative value for the integral, okay, for the function. But, you know, the simplest ones to choose are left, right, and the midpoint, okay? The midpoint is located at right in the middle, a plus b over 2, okay? So if you take the midpoint, f of a plus b over 2, it gives you this integral. So b minus a times f of a plus b over 2, okay? Gives you that integral. Now, this entire idea of approximating the function by a constant goes back to a fundamental theorem in calculus and for the integrals, that there's always a value, okay, for any function, there's a value in the interval a and b, such that the integral of a from a to b is equal f of that value times b minus a. But that value is impossible to find, you know, for arbitrary functions. But that's kind of the idea where this comes from. Now, what is the problem with the midpoint rule? So now, for a continuous function, we can evaluate that function at any point in the interval because it's continuous. But what about discrete data? What if you have your data at the CO2 emissions at 1960, 1961, and 1962? So the midpoint is at 1961. But what if the next point is 1962 and a half? Right? How the heck are you going to find the midpoint with all? What if you don't have a midpoint? Where's your data? Is 1961, 1963, 1964, 1968, you know, 1970, right? It's completely scattered. You cannot really define a midpoint, okay? Unless then you fit a curve or you do a polynomial and then you evaluate that there, but you're not increasing your accuracy by doing that, okay? So the midpoint rule as it is can be problematic when you have discrete data, okay? Can be problematic when you have discrete data. We're going to learn about a better method, the trapezoidal rule, that is as accurate as the midpoint rule, but doesn't need the midpoint, okay? All right, so to do this in Python, you can simply use the integrate module from SciPy. Okay, and in the integrate module, there's a routine, there's many routines. The simplest one I would use is called quad for quadrature. And it's just a general routine that computes the integral of any function, okay, between the interval and the interval AB. And that's the function signature, integrate.quad. You give it your function name, which you would have defined as a Python function. It takes one argument and returns a value. And it does some magic behind the scenes, really great routine. But that works for continuous functions. Okay, we haven't talked about discrete data yet. Okay, we're going to work with continuous functions first, because they're easier to deal with. Okay. So in summary, these are the three rules that we learned so far. Very simple idea. Over an interval, you approximate the function as a constant, either the left point, which is f of a, the right point, f of b, and the midpoint, f of a plus b over 2. Okay. So now we're going to do our first coding activity. Go ahead and grab the notebook Quadrature with Gaps from Canvas under the module integration. And while you're at it, also download the CO2 data.txt. There's a file also there. Put them next to each other. Okay. Go ahead and fire up your Jupyter notebooks. And we'll work together on filling those gaps. It should look like this. You missed a quiz. Let's look in the nano tab. Oh. You all got that notebook? Anyone still working on getting it? While you're at it, grab the CO2 emissions data. It's a text file, txt. Okay. Sure. Anyone still working on it? All right, let's get started. Looks like no. Okay, great. Okay, so go ahead and execute this boilerplate. Okay, activity 1, develop a. Okay, so I actually forgot to tell you kind of what we want for the routine, what we want to do, and that is window. Okay, and the question is to compute, develop 3 Python routines that implement the left point, right point, and midpoint formulas. The routine arguments must include a function or a function name and the interval a and b on which the function is to be evaluated. So first create those routines, 3 of them, call them left point rule, right point rule, midpoint rule, whatever. And then use those routines to evaluate the function, evaluate this integral from 0 to 1 of 1 plus 0.5 sin squared 1.75 pi x, okay, between 0 and 1. So I have some things ready for you here. First, we define the function. I call it my f, my function, and it takes a single value and returns a single value, which is 1 plus 0.1/2 sine 1.75 pi x squared. And first thing you do when you got something, all of you got that answer right on the exam. Flirt with the data, plot it. I was so excited. And when in doubt, print it out. You all got it. So mission accomplished. Good for you. Okay. So, yep, that's the function. And we need to evaluate this, to calculate this area under this curve. Okay. So now I have a couple of 3 functions here, left rule, right rule, and midpoint rule. Okay. All 3 of them take 3 arguments. The function f, function name, What I want to apply to our function, you just pass my f over here, and then a and b, the interval. So go ahead and implement the left point rule, right point rule, and okay, so these are our fancy rules. Okay. So replace the question mark with something. Okay. Good work. All right. I have a lot of coding superstars in this class. A few years ago, this was not the case. When I took over the course and caused a big mess by switching to Python, everyone hated me, from the students and the faculty, half the faculty. But now, it propagated throughout further upstream, and now everyone comes in with more exposure to Python, and it seems like you all are getting better every year. I see new batch of students getting better. Maybe next year I'll switch to Ruby or something else. All right, so looks like most of you got this. Anyone struggling? Happy to help. Okay, just very simple, right? It's going to be b minus a. For the left point rule, it's going to be b minus a times f of a. For the right rule, it's going to be b minus a times f of b. And for the midpoint rule, it's going to be b minus a times f of a plus b over 2. All of it, okay? And what I got here is the application of those rules on my function f. So you just simply pass my f. And when it comes here as something called f, and then it applies it wherever it needs to apply it. And you'll see I picked this function to resemble the red curve that I was showing in the slides, because one of them is going to underestimate the integral. It looks from the graphics. The other one is going to overestimate it. And the midpoint is going to be like right there in the middle, okay? These are the three values. Now, I didn't have a gap for quad, for the exact one. How do you verify your implementation? Okay. You compare to another routine. You either do something by hand, for example, or you compare to another routine. So in this case, we kind of want to get an idea of where we're at in terms of this answer. Clearly, taking this huge of an interval, we're committing a huge error, assuming the function is constant over such a large interval. I mean, the function might be constant over a very small interval, right? But over a large interval, we're committing a huge error. So we can measure that error by taking a more accurate method, which is going to come from integrate, okay? And in integrate, I'm going to pass it dot quad, going to pass the function, which is my f, from 0 to 1. And when I evaluate that, it returns two things. So this quad routine is a general quadrature routine. It did the numerical integration, and it returned a result of 1.272 or 1.273 with an error on the order of 10 to the minus 12. Okay, that's a pretty accurate routine. And that tells us, we're actually the right point rule in this case was a little bit more accurate than the other two rules. But it's really a bad idea to use a constant over such a large interval, especially when you have a lot of variation in the function, right? So if you look at that function, there's a lot of variation going on here. We can be a little bold and increase the frequency of that function and mess up that integral. So we can do that. How do you increase the frequency? Let's make this like 10. Right? So we've increased the frequency of that function. Okay. Now my hypothesis is that our integral formulas are going to be quite off. Okay, because the left point rule is going to be here. It's going to miss all of those peaks. And the right point rule, the same thing. The midpoint rule, I don't know, it might be over here or over there. Who knows? If it's over here, it's going to miss all of the peaks. If it's up there, it's going to overestimate because it's going to pick up all of those troughs. Okay? So let's see. We run it again. We got 1, 1, 1, right? Because it just happened that the midpoint was at the bottom, right? So we got 1 by 1. But quad gave us 1.25. Okay? Okay. Now we can switch back to the slides, right? And see kind of how we can make this better. Okay. Now, obviously, it's kind of a little bit silly, really, to take the entire interval and assume the function is a constant over that entire interval. But you do that when you are on an airplane and you only have like an envelope and you want to do like a quick calculation by hand, okay? But if you have a computer in front of you and you can actually do some more calculation, why not take that big interval AB and split it into smaller segments, 10, 50, 100 segments, 1,000 segments, and apply the same rule to each one of those subsegments. In the end, the integral of f of x from a to b is equal to the integral of f of x from a to a1 plus the integral from a1 to a2 plus the integral from a2 to a3 all the way to the end, right? Visually, this would look like this. If you had this entire interval, rather than taking this entire interval, especially if the function has a lot of variation, why not split it into smaller intervals and apply the same formulas, the left point, the right point, the midpoint? You can do that, right? You just change the interval. Rather than going from 0 to 1, you're going from 0 to 0.01 maybe, and then from 0.01 to 0.02 and so on. And you simply add them all together. And that's really what quadrature is. You're drawing quadrilateral elements under the curve and adding their areas up together. Okay? For the midpoint rule, for example, going from A to B, it would be like, you know, if you split A and B, x to x1, x2, x3, and so on, the formula would look like this. Now, programmatically, it's kind of much easier. And that's what we're going to do next. Okay? So now you're going to develop a Python routine. Okay, so here's how I'm dividing the interval from A to B. I'm calling it x1 to xn. Okay? I should have called it xn plus 1 because we need to distinguish between points and segments. We're going to say we're dividing this into n segments. Okay, so you have n plus 1 points. Okay, I'll fix this. Let me see if I can fix it just now. Okay, xn plus 1. Okay, there you go. Okay, fixed. So you got n segments, n plus 1 points, but n segments. Okay, and you're just simply looping over these n over each segment and applying either the left point, the midpoint, the right point, or the midpoint rule. Okay, and that's going to be our next coding activity. And the critical hint here is, okay, this is going to be a subroutine that takes in the function f, whatever function, the interval a to b. Okay, so f, a, and b. But we also need potentially one more argument, which is the number of segments. Okay, so I want to say I want this routine to evaluate this integral with 50 segments. Okay, that's similar when we did iterative solvers and we told it to do a maximum number of iterations, right? Remember that? Okay, so let's switch to our Jupyter notebooks. develop a Python code that computes the integral for an analytical function with the arbitrary number of points, intervals n. Use the left point, right point, and midpoint rules. Okay. So here I declared 3 functions for you. They're all similar, so I'll only look at the left rule with you. It takes in a function f, left hand side of the interval, the right hand side of the interval, and the number of segments. So you have to be clear what n is. In this case, we're defining n as the number of segments. So first, what I'm going to do, I'm going to create a linear space for the points that are going to define the segments, right? Because every pair of points is going to define a segment, and I'm going to use that lint space as my segments, and then I loop over each segment and apply the left rule, right rule, etc. So first, you got to figure out how to create this lint space. Clearly, it goes from A to B, and how many points you want to put in here. Then we declare an empty result. So we put 0 in it because that's the answer for our integral. We put 0 because we're going to be adding values to it. So, okay, we start with 0. And then you go, you have to loop over the segments or the points, however you want to define this. And then for each segment, the A of that segment is the point to the left, so it's xi. The B of the segment is xi plus 1, and then you apply one of the rules. Okay, so go ahead and try that. Do it for once you figure it out for the first, you'll figure it out for the other. So pick one, the left, right, or the midpoint rule, and work on it. Okay, you can work in groups. So over here, I put a comment. It's better to loop over the segments. Okay, it's better to loop over the segments. Okay, you have n segments, so you know what your range is. Okay. Excuse me. Got it. For I in range AB. Yes, Paula. No. Sorry. If you're in doubt, yes, create a new cell, and create a lint space and play with it. Okay, so put a lint space and say going from 0 to 1 with 10 points, right? And see what happens. Okay. So one other thing to think about, if you have 3 points, how many intervals do you have? 2 intervals. You have 5 points, you have 4 intervals. You have 50 points, you have 49 intervals. Okay. We're passing the number of intervals, not the number of points. In the end, it's not really going to make a big difference. So we're taking that interval A to B, and we're splitting it into points. Okay. So, and we're going to accomplish that with a linear space, right? So I really want If A and B are like 0 and 1, I want 0, 0.01, 0.02, 0.03. So we're using linspace to create that. So think about the linspace, start, stop. Where does it start from? Where does it go to? And how many points do you need in that linspace to define n segments? So what do you think went wrong here? You have a few mistakes, but the most of them, the first mistake is benign, but the second one is a big deal, right? So ask yourself, you created 50 segments here, let's say, okay? What did you do in the range? The range is simply an iterator, a counter, 0. So go ahead and print for I in range 0 to 1 and print out I. What are you going to get? You're going to get 0. You're going to get one interval. Well, no, don't blindly try things. What is range? What does range do? It's a counter, right? It's an integer counter. It just gives you 0, 1, 2, 3, 4, 5, 6, 7, 8. So we need to go over the first segment, the second segment, the third segment. So you need to count the segments. You need to go over the segments. Yeah, X is the actual abscissa, right? It's the actual abscissa. The range is simply a counter. It's a helper. It helps us count things, okay? Okay, so I see a lot of healthy conversations. Okay, anyone ready to help us out? Paula, you want to take this on? All right, so let's start. Which one do you want to do? The left rule, right rule, left rule. Okay, so first we start with linspace. Okay, what do you? Yes, thank you. Very good. So why did we use linspace? We're not plotting or anything. We just used linspace to allow us to take that interval AB. Let me show you on the slides. To take that interval AB and split it into x1, x2, x3, x4, and so on to xn plus 1. But by definition, we said we want n to mean the number of segments, not the number of points. So in linspace is based on the number of points. Okay, so for n segments, you need n plus 1 points. Okay, and n is an argument into the function. Okay, so if you're in doubt, you go ahead and print it out. So if you take linspace, let's say from 0 to 1, and let's say you want so let's say you want 10 segments. If you put 10 here, you're not going to get 10 segments. What you'll get, let me scroll this down a little bit so my hands can reach. You'll get first segment between 0 and 0.11. So 1 segment, 2 segments, 3 segments, 4 segments, 5 segments, 6 segments, 7, 8 segments, 9 segments. You didn't get 10 segments. So to get 10 segments, you need n plus 1. So you put 11. Okay. So now that will give you 10 segments. Okay. So then for n segments, you need n plus 1 points. So now x defined the sub-intervals for us. The difference between two consecutive x values gives us the new b minus a, the b minus a for that segment. Okay. Now the next step, so if you look at this, once we created this, the next step is, I mean, you can do it in 1,000 ways. But the way I want to do it is I want to loop over the segments. I want to say, okay, my first segment, my second segment, etc. Okay. So how do you do this? I'm going to create a counter that goes over the number of segments. And I can accomplish this with range. Okay. So we create a range from, who wants to take the range? Jake? Okay, from 0 to n. It's simply a counter, so from 0 to n. Okay. Now again, if you're in doubt, go ahead and print it. If you're confused, you forgot what range is, it happens. We all get old. Okay. Okay, I always forget. Okay, for I in range from 0, let's say, to 10. Okay, it's just a counter. It's starting from the first point to n minus 1. So that gives you the number of segments. Why didn't we put n minus 1? Because we're starting from 0. You could have started from 1. You would have to go from 1 to n plus 1, because that gives you n segments exactly. But because I know my arrays are 0-based, I'm going to start at x0 to access the first x value. So it's just easier to start from 0 to n. Start from 0. Okay. So now, as I'm looping over the segments, we start with the 0th segment. The a value for the 0th segment, or the left value, is xi. And the next value, b, is xi plus 1. Okay, it's just simply the next value, xi plus 1. Okay, now for the left rule, becomes simple. You just do b minus a times f of a. Okay, that's the left rule. And notice here I'm saying result plus equal. So what that means is result equal result plus this. So we're adding up all these approximations. As I changes, you're going, so you start with I equals 0. So I should probably change the nomenclature here. For I equals 0, you get x0 and x1. So that makes this the 0th interval. For I equal 1, you get x1 and x2, and so on. And you add them all up. Okay? The rest is similar. Again, from A, we go from A to B and n plus 1. And the range from 0 to n. So xi plus 1. And this is the right rule. So we get b minus a times f of b. What's nice is that you have the function. You can evaluate it anywhere you want. A, b, n plus 1. And for the range, we have 0 to n, xi plus 1. And then result, you get b minus a times f of a plus b over 2. Done. All right, so now look at how accurate this has become. Now, I did change the frequency here, so I'm going to go back to 1.75. Remember, quad gave us 1.272. Okay, I don't know however many intervals it used, but look at this. Whether you use the left rule, right rule, or midpoint rule, you're quite in the ballpark. Because as you shrink that interval, the function, yeah, can be reasonably approximated by a constant. Okay. Okay, we're ready to go back to the slides. I can always count on you, Nathan, to All right. So now the question is, what if we had discrete data? Okay. Which of these rules do you think applies just readily, easily? Left, right, or midpoint? Why and why not? Okay. So the left point rule applies readily because you're going through your data, whether they're equally spaced or not, doesn't matter. You take the left point and do the difference on the x-axis. That gives you this side times the y value at f of a, and you're good to go. Same thing for the right point rule, right? See the difference between the left and the right point rule. Okay. Now, the problem is the midpoint rule. Does it apply and under what conditions? Rich. Pardon me? Yes, but what if they're not equally spaced? Then it's not a midpoint rule anymore. It's the tertiary rule or whatever. Maybe the point, in the middle is like at 1/3 of the interval or whatever, right? So it's not really the midpoint rule anymore. Okay. So it's not readily applicable unless the data is equally spaced. If it's equally spaced, you can go over every other point and take the midpoint and apply the rule, and you're good to go. Okay. That's the challenge with discrete data and these rules that we just described. Okay. Now we're going to learn about a much better rules. You don't have to worry about the midpoint rule anymore. Okay. So now we're going to take this CO2 data. Now we're equipped with a bunch of rules to be able to evaluate discrete data. Okay. And the idea is use the left point and right point rule. We're not going to do the midpoint because the logic is going to be a nightmare to try to skip over every other point, find the midpoint. We're not going to do that. We're just going to apply the left point rule and the right point rule. You already have your intervals defined over here. Okay, so all you're doing is looping over the data that you're given. And we're going to build a routine that computes the left and right point rule to can approximate the integral under this curve. Now in Python, you cannot use quad, integrate.quad on discrete data. But NumPy has a very famous routine called TRAPZ, which stands for trapezoidal, okay, trapezoidal rule. We will learn about the trapezoidal rule in the next slide. Excuse me. But that's what we're going to use to compare our calculation to something else. Okay, so let's go back to your notebook. Sorry. Okay. So first, we're going to load the data. Don't worry about what I'm doing here. I'm just, getting you the data. The data is going to be given to you as xi and yi data. Okay, that's your data. You have the xi values in 1960, 1963, whatever, and the y values, which correspond to the CO2 emissions. Okay. Where's my cursor? So when you grab this, this is the data. Okay. So we got the data. First thing you do, you plot it. Okay. Labels, etc. So this is the data. Okay. So now I have skeletal functions for you to do the left rule or the right rule on XY data. Now you don't have a function anymore. You don't have a number of segments anymore. Okay. Because the segments are already predefined for you, right? So all these functions are taking are X and Y discrete data. Okay. You see here in the function definition, left rule 2, or discrete, whatever you want to call it, it takes XY. I start with a result of 0 for my integral, because I want to add up all the areas between these points. And now I'm going to loop over the data points. Okay, we're going to loop over the data points. So go ahead and think about how we're going to do that. I did take the number of points as the length of the array X or the length of the array Y. It doesn't matter. So you have that N. You have your number of points N. Okay. So now we're changing on loop over segments or points, however you want to think about it. Okay. So take a second and think about how you might want to do that. It's very similar to the previous one. Okay, you have n points, len x, and you're going to loop over the segments or the points. Okay. I'm floating around if you need help. Yes, I'm like so advanced. You should teach the class. You got it? How can I help? Well, no, yeah. This is. Oh, okay. So, it gave you an error. Index 55 is out of bounds. So what that means is you've probably reached a point that doesn't exist. You're trying to access a value in the array that doesn't exist. And where is that happening? It's in these guys, right? These three guys. I doubt it's the xi or the yi. It's probably going to be this guy.
Yeah.
So your I, when it reaches the end, is going out of bounds. So maybe your range is messed up, right? So if you have n points, how many segments do you have? N minus 1 segments. And the range, if you're starting from 0, to get n minus 1 segments or n points, if you're starting from 0, you gotta go from 0 to n minus 1, right? So try that.
How difficult is this to implement across 3 dimensions? And would you use these?
Oh, yeah, it's a different story in 3D. It becomes a little different.
Is there simple methods like this?
Yeah, but then you would have to discretize the plane into kind of little squares, right? And then evaluate, assume the function is constant over that square. So it becomes a little bit kind of more involved, but it's doable. Yeah.
Also,
Yeah.
like the traffic light,
Plane. Yeah. Trust me, I'll be the most hated person if I do it in 2D and 3D. Please, Nathan, please. I'll just give it to you as a homework assignment. You too. No, just like, no. Don't get me involved in this. I'm not, I don't know you, sir. Okay. Some got it, some not. Your problem is going to be in the range. The meaning of that range. Where are you going to go? From 0 to what? You guys got it up there? Okay. Who wants to help? Who would like to help? Go ahead. Why? Okay, but your range function goes to the end point minus 1, right? So you're going to n minus 2, but you're starting from 0. So it's n minus 1 intervals, right? If we started our range from 1, we would go to n, right? Okay, so that's correct. So we go from 0 to n minus 1, and that's really it. Your a is simply xi. Your b is xi plus 1. Your f of a is the y value at xi or at A. So it's yi. Okay, y at I. Y at I. Same thing over here. Range from 0 to n minus 1. Your A is xi, your B is xi plus 1, and your f of B is yi plus 1. Right? That's the right point. And then you do this calculation and you get 232 or 233, you know, depending left or right rule. And we can do the trapezoidal rule from Python, from NumPy, np.trapz. Okay, now trapz takes y values and x values. Okay, that's it. That's all you got to give it. Okay, so I'm going to give it yi and xi, and produces 232.88. Okay, Paolo, you had a question? You have a different what?
Went wrong somewhere. Just give me that.
Scroll up. You guys have a different
I think so.
yeah. Okay, so you might have a different data set. Maybe I have an updated data set and I gave you the old data set, but that's okay. Hey, look, if it's consistent with TRAPZ, then it's good. Okay. I probably have one more data point over here. So hold on. Let me see. If I print xi, I got until 2016. Yours is to 2014. Yeah. I was trying to cheat you with a couple of data points. That's good. Thank you for pointing that out. Okay. Now on to some more advanced rules. Okay. All right. More accurate methods, the trapezoidal rule. Now we started by approximating the function as a constant over an entire interval. Okay. A more accurate representation would be to approximate it as a straight line. Okay, so you just draw a straight line from A to B. Okay, draw a straight line from A to B and integrate that straight line. Okay, so now I'm asking you to calculate the area under this line between A and B. Okay, so if you were given a straight line between A and B, so A, whatever, alpha x plus beta, okay, and you can figure out what alpha and beta are, okay, integrate to the integral of that straight line analytically, because that's how these formulas are developed. So integral of alpha x plus beta dx from A to B, and then figure out alpha and beta later, what the slope or intercept are. Or you can do it using geometry, Evan. Can draw one. Yeah, so split that area into a rectangle and a triangle, a right-hand triangle. Okay. In 3D, he's you got it. Yeah. Okay. Isn't this cool? Doesn't depend on any midpoint, right? Only depends on the endpoints. Come on, just try to integrate or use geometry to do it. Add up the area of the rectangle from A to B and f of A, and then the triangle above it. Yeah. Or the area of the trapezoid. I like to complicate things. Or the area of the trapezoid. Which is what you did, right? The area of the trapezoid. Yep. And so now prove that it is equal to the area under the straight line. Okay. you can simply calculate the area under this trapezoid as b minus a over 2 times f of a plus f of b. Okay? If you don't remember the area of the trapezoid, do a rectangle and a triangle. You can prove to yourself that this is equal to the area of the straight line passing through A and B. Okay? Now, how cool is this method? First, I know from a later slide, because I created that slide, that this method has a smaller error than the midpoint rule. So the left and right point rules have the lowest errors. The midpoint rule is the next best, but the trapezoidal rule is even better. And yet, what is its advantage to the midpoint rule? There's no midpoint. Exactly. All we need are the bounds. So we can apply it equally to tabulated data that's not necessarily equally spaced, and also to continuous functions. That's why it's one of the most popular methods out there. Okay? All right. So now that's the trapezoidal rule. So now I'm asking you, calculate the error in integrating the function y equal 2x plus 3 on the interval 0, 2 using the trapezoidal rule. Who's got the answer in a second? Kara. Yes, there's no error because the trapezoidal rule approximates a function by a straight line. But if the function is a straight line, that approximation is exact. So there's no error. If your function is a straight line and you're using the trapezoidal rule to calculate the area under that function, there's no error. Okay? Because the trapezoidal rule is exact for a straight line. Okay, now what is the error in integrating y equal constant on the interval a, b using the trapezoidal rule? If you say 0, you better back it up. And don't look at the next slide. Go ahead.
It's also 0 because the average of the 2 points is the same. So it would just end up being.
Okay, that's one way to look at it. Correct. So the straight line, a constant function is a straight line with 0 slope. Now the trapezoidal rule is exact for a straight line. It's also going to be exact for a constant. Okay. So it's a rectangle, right? So the error is 0 because the trapezoidal rule is exact. These are the kinds of questions you would expect on an exam from me. Okay. Okay. Simpson's 1/3 rule. So we're just kind of surveying all of these rules. They're just, you can come up with your own rule. All of these methods, all that they're doing is they're taking an interval and approximating the function by a polynomial. We started with a constant. Next, we did a straight line. What are we going to do next? Quadratic, right? So approximate the function as a quadratic on the interval AB. This is a quadratic. It's kind of, you see kind of the curving up a little bit, okay? But it is a quadratic. And then you simply, for a quadratic on the interval AB, you need 3 points, right? Because you have A, B, and C. Okay, for a quadratic, ax squared plus bx plus c, or whatever, when we did polynomial interpolation, a0 plus a1x plus a2x squared, you needed to find those 3 unknowns, a0, a1, and a2. Okay, so you need to pass an interpolant between 3 points. So you have to create a point between A and B. Now that's annoying because now you have to know a point between the 2 endpoints, which makes it useless for tabulated data, or not very useful for tabulated data. But for continuous functions, it's pretty useful. Now you can pick this point anywhere you want, the point in the middle. Okay, you can pick it at 1/3 of the way or 1/3 of the way from here. The best one, or the kind of the non-biased one, is to pick it in the middle, right in the middle, at a plus b over 2. And then the Simpson's rule gives you this formula. Delta x over 3 which is b minus a over 3 because you split this into, sorry, delta x is b minus a over 2. You split this into 2 interval or 3 points. So you get delta x over 3 times f of a plus f of 4f of a plus b over 2 plus f of b. It's simply the integral of the quadratic that passes through these points. Okay, so it's a very simple math problem. You pass a quadratic of the form alpha x squared plus beta x plus gamma. You pass it through a plus b over 2, and b. You find the coefficients, you integrate by hand, and you get that formula. Okay, so now what is the error in integrating y equal alpha x squared plus beta x plus gamma on the interval a, b using Simpson's 1/3 rule? 0. Why? Because, yes, because the Simpson's 1/3 rule is exact for a quadratic. Okay? Now there's one more rule, Simpson's 3/8 rule, and it puts a cubic. And we can go on forever. I'm not going to do that. I can have 1,000 slides. We can fit as many functions as you like in an interval, but these become useless for discrete data. They're only very useful for continuous data, because continuous functions, because for a cubic I need 1, 2, 3, 4 points. Okay, so, and I pick those points over here, like equally spaced. You can do this for discrete data, but if it's not equally spaced, then you have to fit a cubic between every 4 points. It's going to become a nightmare. You have to solve a system of equations for every 4 points and integrate. Don't do that. Okay, use the trapezoidal rule and be done with it. It's not going to give you any more, any significant improvement. Okay. So again, the formula here, you have these 4 points, x0 or a, x1, which is at b minus a over 3, because you have 3 segments over here, and just becomes a moot point to kind of repeat all of this. But it's a little more accurate. And then I ask the question, if you're approximating a cubic with Simpson's 3/8 rule, then your result is going to be exact. You're going to have, your error is going to be 0. Okay. This is a summary slide that you'll carry with you in your pocket as you go through life, or not. It's a little summary slide, right? You know, you'll find this information on the internet, on Wikipedia, on Google, whatever, right? But if you need to kind of remember this in the future, this is it. Okay. So again, we can apply these concepts, some of them to tabulated data, but definitely to continuous data. And we already answered the question that of these 3 rules, the trapezoidal rule, the Simpson's rules, the one that applies readily to discrete data is the trapezoidal rule, right? Because you only need the endpoints. The other ones, if it's equally spaced, then you're good to go, but you have to kind of skip over every other point. Okay. All right, so we'll have to finish this up next week because there's a little coding activity. There's like 5 more minutes, but we'll start next week, next Thursday, on Thursday with those, and we'll finish this up and we'll do differentiation. Okay, thank you.